Today I will present journal club presentation about supervised machine learning. This research is based on comparative study of 4 supervised machine learning techniques for classification, authored by Mohamed. They are from the University of Essex. It was published in the International Journal of Applied Science and Technology in 2017. This study focuses on evaluating the performance of 4 supervised machine learning methods. They are decision trees, k-nearest neighbor, KN, artificial neural networks, ANN, and support vector machines, SVM, using various performance metrics, including accuracy, sensitivity, specificity, and kappa statistics. In this slide, I will briefly explain the 4 machine learning methods we evaluated. First of all, decision trees. This method operates by splitting the data into branches based on feature values. The process continues recursively, creating a tree-like structure where each internal node represents a decision based on a feature, and each leaf node represents a classification. One of the key strengths of the decision trees is their simplicity and ease of interpretation. They resemble a series of if-then statements, making them accessible even to non-experts. However, decision trees are prone to overfitting, meaning they can perform very well on training data, but might struggle to generalize to new unseen data. To mitigate these techniques, like pruning or setting a maximum depth, are often employed. Another one is k-nearest neighbor, KNN, is a non-parametric instant-based learning algorithm. It works by identifying the k nearest data points to the instance we are trying to classify and then assigning the class label based on the majority vote from these neighbors. The algorithm is quite intuitive and does not require a model to be built beforehand, making it useful in cases where we want to perform quick predictions without an elaborate training phase. However, KNN can be computationally expensive, especially for large datasets, because it requires calculating the distance to every point in the dataset for each new instance. Moreover, the choice of the value of k and the distance metric used can significantly affect the performance. Another one, artificial neural networks, ANN, is inspired by the structure of the human brain, consisting of layer of interconnected neurons. These networks are especially powerful when it comes to recognizing complex patterns and relationships in data, particularly for nonlinear problems. ANs can learn these patterns by adjusting weights through a process known as propagation during the training phase. However, they require large amounts of training data and computational resources, and the training process can be time-consuming. Additionally, AN can be difficult to interpret because they function as black boxes, meaning that it's often hard to understand exactly how a particular decision was made by the network. And last one is about the support vector machines, SVM. Is a powerful supervised learning algorithm that works by finding the optimal hyperlane that best separates the classes in the feature space. The goal is to maximize the margin between the classes, which helps to ensure that the classifier generalizes well to unseen data. CVMs are particularly effective for both linear and nonlinear classification tasks. For nonlinear cases, CVM can use kernel functions such as polynomial or radial basis functions to map the data into a higher dimensional space where the classes are more easily separable. However, the performance of CVM is highly dependent on selecting the correct kernel and its parameters, which requires careful tuning. Despite this, CVMs are known for their robustness and effectiveness even with smaller datasets. In this slide, we will review the key evaluation metrics used in this study. The dataset sourced from the UCI repository consists of 1,000 instances with 24 attributes split into two classes, good and bad. We used several metrics to assess classifier performance, including accuracy, confusion metrics, ROC curves, and the kappa statistics. Accuracy measures the proportion of correctly classified instances across the total. The confusion matrix helps break down true positives, false negatives, false positives, and true negatives, giving a more nuanced view of performance. Another one is ROC curve, shows the trade-off between true positive rates and false positive rates, and the area under the curve quantifies this. Lastly, the kappa statistics compares the classifier's performance to random guessing. A higher kappa value indicates better consistency with actual level. These metrics together help us get a comprehensive picture of the classifier's effectiveness in different scenarios. Let's look at the performance comparison across the four machine learning methods. The support vector machine achieved the highest accuracy at 76.3%, outperforming decision trees ANN and KNN. When considering sensitivity and specificity, KNN showed the highest sensitivity, meaning it was most effective at identifying true positives, while ANN was better at specificity, detecting true negatives more accuracy. Finally, the kappa statistics further emphasize SVM's consistency as it outperformed the other methods in this measure, indicating better alignment with the actual data labels. The ROC curves presented here visually confirm that each method has its strengths, with KNN and ANN showing strong performance in sensitivity and ROC areas, while SVM is most balanced performed overall. In conclusion, this table summarizes the performance of four classifiers. Support vector machine achieved the highest accuracy at 760.3% and had the best kappa statistic, showing it was the most consistent across the board. It also excelled in sensitivity, making it the most effective for detecting true positives. Artificial neural networks showed strong specificity, meaning it was better at identifying true negatives. Decision trees had balanced performance across the metrics, but didn't outperform SVM. K-nearest neighbor, while highly sensitive, struggled with specificity and the lowest kappa value, reflecting less overall consistency. Ultimately, while SVM demonstrated the best overall performance, the results highlight that no single model performed best across all metrics, and the choice of classifier depends on the specific requirement of the task. Thank you for listening.